Today, we're going to dive into one of the real workhorses of quantum computing, the quantum phase estimation algorithm. You'll often hear it called QPE. Now, it's not the kind of algorithm that gives you a final answer all by itself, but trust me, understanding it is absolutely key to unlocking some of the most famous and powerful algorithms out there.
So, right off the bat, this is the main thing to get about QPE. Its power isn't in what it does alone, but in its role as a subroutine. Think of it less like a finished car and more like the incredibly powerful engine inside. It's the component that makes the whole machine go, enabling those other, more famous algorithms to do their magic.
All right, so here's our game plan for this explainer. First, we'll talk about its role as the algorithm's algorithm. Then we'll get into what quantum phase even is. We'll see how it works with a simple one-qubit example, then look at how we get more accurate. And finally, we'll see why it's truly the keystone of quantum power. Okay, first up, let's really nail down this idea of QPE as a tool for other tools. It's not the end product, it's the high-performance part that you plug into a bigger machine.
And, just for a little context, this isn't some brand new idea. We have to go all the way back to 1995, when the physicist Alexei Kitaev first introduced it. So yeah, this has been a fundamental building block of the field for quite some time now.
This is where you really see its muscle. QPE is the secret sauce inside the heavy hitters, like Shor's algorithm, the one that could break a lot of modern encryption, and the HHL algorithm for solving huge systems of equations. It's a fundamental piece of the toolkit for going after some of the gnarliest problems we can think of.
All right, so we've covered the what. We know it's a powerful subroutine. But to really get the how, we've got to ask, what on earth is this phase that we're trying to estimate? Let's decode it. Okay, let's dust off a little bit of linear algebra here. Imagine you have this special vector, and when you apply some transformation to it, it doesn't get knocked off its line. It just gets stretched or shrunk. Well, that special vector is an eigenstate, and that stretch factor is its eigenvalue. In quantum computing, our gates are the transformations, and QPE's whole job is to figure out that eigenvalue.
Now here comes the quantum twist, and this is super important. For the gates we use, these unitary operators, the eigenvalue always has a length or magnitude of 1. So if you were to plot it, it would always land somewhere on a perfect circle with a radius of 1. And what's cool about that? It means you can describe it perfectly with just an angle. We call that angle theta, or, you guessed it, the phase. So the crucial takeaway is this. Finding the eigenvalue is finding the phase. They're the same problem.
But hang on a second. You might be thinking, so what? Because if you take two quantum states and the only difference between them is their phase, their measurement probabilities are identical. The phase is basically invisible when you look at it that way. So why are we building this whole elaborate algorithm just to find it? The answer, in one word, is interference. While you can't see the phase in a simple measurement, it becomes everything when quantum states interact. Think of them like waves. The phase tells us whether those waves are going to add up and get stronger, amplifying the right answers, or if they're going to cancel each other out, getting rid of the wrong answers. This is the whole magic of quantum computation. And phase? Well, phase is the control knob. So we know why we need the phase. Now for the fun part. How does the algorithm actually find this hidden number? We're going to start simple, with just one qubit, to see the core trick of the whole operation. And that trick has a fantastic name, phase kickback. Phase kickback is one of those wonderfully weird quantum effects. You set up a controlled gate, and you think you're about to apply an operation to your target qubit. But nope, the universe plays a little trick. The phase that was supposed to go on the target gets kicked back up to the control qubit instead. And this isn't just a weird quirk. It's brilliant. It's how we take that hidden phase information and move it to a place where we can actually see it and measure it. Okay, let's walk through this step by step. We start with two qubits. One is our counting qubit, which is going to store the phase, and the other is our target. We get them ready, then we put the counting qubit into a superposition with a Hadamard gate. Now for the magic. We apply a controlled Z gate. And this is where the phase gets kicked back from the target onto our counting qubit. Then all we have to do is take the counting qubit out of superposition and measure it. And bam! The result of that measurement gives us the phase directly. For this specific example, with the Z gate and the 1 state, the phase theta turns out to be exactly 0.5. We did it. We successfully pulled that hidden number right out of the quantum state. Now, that one qubit example was cool, but let's be real. The universe isn't always made of nice, clean numbers like 0.5. So what happens if the phase is something messier? Well, to get a more precise answer, we just need more horsepower. In this case, more qubits.
The way we get more precise is by thinking of the phase as a binary fraction, like 0.1011. The QPE algorithm is designed to figure out those digits after the decimal point. And here's the key. Every single counting qubit we add to our setup lets us find one more of those binary digits, making our estimate better and better.
And you can see how this scales up really nicely. If you just need a precision of 0.5, one counting qubit is enough. But if you need to narrow that down to 0.25, you're going to need 2 qubits. Need to get even finer, down to 0.125? Well, that'll take 3. The relationship is so direct. You add a qubit, you double your precision. It's as simple as that.
But of course, this is quantum mechanics, so there's always a fun little trade-off to think about. It's not just about how accurate your answer is, it's also about your probability of success. There's this really interesting push and pull that connects how many qubits you use to both the precision you want and the chance that you'll actually get the right answer when you measure. Let's make this real. Imagine you have 6 qubits to work with. If you get greedy and tell the algorithm, I want 4 bits of accuracy, well, you're only going to succeed about 60% of the time. But if you relax your standards a little and say, you know what, 3 bits of accuracy is fine, your chance of success shoots up to 90%. So if you want both super high accuracy and a high probability of getting it, the answer is simple. You just got to bring in more qubits.
And that brings us right to the end. Let's tie all of this together and really appreciate why quantum phase estimation is so incredibly fundamental to the whole field.
So if you're going to walk away with anything, let it be this. 1. QPE's whole job is to find that hidden phase, or eigenvalue. 2. It does this using that clever quantum trick, phase kickback. 3. If you want a more precise answer, you add more counting qubits. And 4. The biggest point of all, QPE is not the star of the show. It's the foundational keystone that lets the really big, powerful algorithms actually do their work.
Getting your head around quantum phase estimation isn't just some academic exercise. It's like learning how a combustion engine works if you want to build a race car. This is one of the absolute core technologies that could get us to a real quantum advantage. We have this powerful subroutine, this incredible tool, just waiting to be plugged into the next great idea. And that leaves us with just one question, really. What enormous problems are we going to solve with it next?